Have you ever heard of data leakage? So it's a known issue in machine learning in general, and it causes basically us to overestimate the performance of our machine learning models compared to their real-world performance. Unfortunately, this issue has not been super well investigated in the case of knowledge graph embedding-based link prediction. So this is the objective of this study. So when we are training knowledge graph embedding models for link prediction, we start from the we start from an initial set of facts that are included in our knowledge graph, and we will split them into training and test sets, where the test set is used to evaluate our models. When we are actually using our models in real-world deployment, we are using an inference dataset. And so, as you can see, because the training and test datasets are drawn from the same initial data distribution of knowledge graph triples, we have some dependencies between them that do not naturally occur with our inference datasets. And this is what is causing data leakage. So in this study, we wanted to investigate the impact of data leakage on knowledge graph embedding models for link prediction, and we investigated 3 different sources of data leakage. The first one being the easiest one to detect the presence of redundancies between the training and the test datasets. So in a knowledge graph, you can have some redundant, relationships that convey similar meanings or which overlap in some way. So for instance, if you include both protein-protein interactions and more broadly interactions. And so basically, if you don't control for these redundancies, you will have data leakage. So we produced a procedure to automatically detect and remove such redundancies. And we show that if we don't control them, so here we have the 7 knowledge graph embedding models that we investigated. In red, you have the performance when we keep those redundancies, and in blue, when we remove those redundancies. And as you can see, we have an inflation of the performance when we don't control for this first source of data leakage. A second source that we investigated is the use of illegitimate features, and more specifically, we investigated the use of not degree, because not degree can be accessed by the models through the training knowledge graph. So I don't have time to go into the details, but basically we performed a degree invariant permutation procedure on the indication relationships linking drugs to their indicated disease. And so the results are kind of good news. We don't see that not degree is used as a predictive shortcut for our models, but we do not exclude that other illegitimate features might be used, and for instance, access to community structure. Finally, and the most pernicious type of data leakage we investigated is that sometimes your test dataset is not really representative or true generalization capabilities of your model, and basically the test dataset will not be similar to what you will use in inference time. So to test this, we gathered some drug disease indications from the OrphaNet database, and we use this as an inference dataset with ground truth. And so basically, we will compare performance on the test dataset, which is sampled from the knowledge graph, and this inference dataset, which is completely external. So we tried 2 strategies for creating this test dataset. The first one is a classical random split. So in this type of split, you might be trying to predict in your test dataset indications for drug which have already been indicated for other disease in the training dataset. So we also have another strategy, which is the cold start split, which is more strict because in this setting, we will make sure that any indication we are trying to predict in the test dataset is regarding drugs that have never been indicated in the trained dataset. And so we do that both for drugs and diseases. So if we look at the performance on the test set of those random splits, you can see that the cold start setting is less performant, but that's expected. It's more difficult to predict such kind of cold start drug repurposing opportunities. But in any case, if we look at the inference dataset performance, the performance completely collapsed, and you can see that the performance that we obtained in this test dataset is not really representative of what we are going to get in inference time. So basically, our our models completely fail to predict those drug repurposing opportunities from our inference datasets. And that's a big issue because this is a kind of a representative of what we would want our models to do. So to conclude, so data leakage is a big problem in knowledge graph embedding and more broadly in machine learning. So if you are developing your own machine learning models, please take this issue into account. If you are reviewing machine learning papers, ask the authors whether they did any type of data leakage mitigation procedure. Thank you, everyone, and I will be available later for questions.